Hi everyone, this is Sam Ganzfried. I'll be presenting a new algorithm for computing Nash equilibrium in continuous games with application to continuous Blotto. So, successful algorithms have been developed for computing or approximating Nash equilibrium in a variety of finite game classes, even game classes that are challenging from a computational complexity perspective. As one example, there's an algorithm that was recently applied for approximating Nash equilibrium in 6-player no-limit Texas Hold'em that defeated some strong human professional players. This is a very large, extensive form game with imperfect information and conjectured from a complexity perspective to be very challenging, but nonetheless the algorithm was able to compute very strong strategies. Now, continuous games are fundamentally different from finite games. A continuous game, the strategy space, I'll define it formally later, but the strategy, the set of pure strategies is potentially infinite. Now, one difference is that continuous games are not even guaranteed to have a Nash equilibrium. The theorem of John Nash only proved existence in finite games. Another challenge is that we may not even be able to represent mixed strategies in a continuous game because they correspond to a probability distribution over an infinite, potentially uncountable pure strategy space. So there might be a Nash equilibrium, but we might not be even able to represent it, let alone compute it. Now, there are some existence results for certain specialized classes, but these are not going to hold for many important game classes, including the game we're going to see, even for 2-player zero-sum games. Now, strategic form game consists of a set of players, set of pure strategies for each player, and a utility function, Nash equilibrium, the standard solution concept in game theory, and in practice, we're trying to approximate Nash equilibrium. We define epsilon to be the maximum a player can gain by deviating from a profile, and so epsilon equilibrium is, for a given epsilon, we say that sigma star is going to be an epsilon equilibrium. Continuous games are going to generalize these finite games to the case of infinite strategy spaces. Many natural games are going to have an uncountable number of actions. For example, if the strategies correspond to an amount of time, money, or space. And mixed strategies here are just going to be the set of probability measures on the pure strategy space. Now there's one theorem due to Glicksberg that says if the strategy spaces are non-empty compact subsets of a metric space and the utility functions are continuous, then there exists a Nash equilibrium. Algorithms have been developed for computing Nash equilibria in certain special cases of continuous games, for example, separable games. However, we'll see a Blotto game, continuous Blotto game, that doesn't fit in any of these classes. Furthermore, it's going to have discontinuous utility functions, so we don't even have a guaranteed existence of an equilibrium. So Blotto game, it's a 2-player zero-sum game. It's a very well-studied game where players are simultaneously distributing resources over several objects or battlefields. In the classic version, we say, okay, if a player whoever devotes the most resources to a battlefield wins that battlefield, and the payoff is equal to the number of battlefields won or the sum of the values of the battlefields won. This was first proposed by Burrell in 1921 and has been applied frequently to national security scenarios. It's also been applied to voting problems and auction theory models. Now, the initial approaches for Blotto derived analytical solutions for special cases. Then, finally, in 2016, there was a general algorithm. First, it was a polytime algorithm with exponentially sized linear program, which was then improved to a polynomial size. Now, however, these algorithms are just for a discrete version of the game. There's no general algorithm that's been devised for the original version of the game, which was continuous. Now, I'm not going to go over the whole definition of imperfect information game, but basically players have some private information that the other player is not aware of. The existence and complexity results are similar for imperfect information games. Now, Here's our model that we'll be looking at of a continuous imperfect information Blotto game. So there's two players, there's a set of battlefields, there's a set of slots, and then a set of outcomes, which is a subset of the set of permutations of these slots. There's going to be a probability on each of these outcomes. Each of the battlefields is going to have a positive real value, and each player is going to have a budget. So the strategies are going to be how much, so for player one, it's going to be how much resource to allocate to each of these slots, subject to being within the budget. And for player two sees which battlefield is in which slot. And so for each of these outcomes, player two is going to pick an amount to allocate for each slot, subject to the budget constraint. And there's a parameter delta where essentially player one, if player one puts more resource in a slot than player two by more than delta, more than or equal to delta, player one's going to get the value. Otherwise, if player two puts more than or equal than player one does, then player two gets the value and player one gets negative value. Otherwise, they're both going to get 0 if they're within delta. This is just sort of repeating that. The game is zero-sum because the payoffs sum to 0, and this game has asymmetric imperfect information. Note that the utility function here is discontinuous. It can shift abruptly between the value 0 and negative the value, and so it doesn't satisfy the condition of the theorem I mentioned, doesn't apply, doesn't fall in other specialized classes, and so there's no guarantee that this even has a Nash equilibrium, and there aren't other algorithms that apply. Often, let me just briefly mention why we include this delta term. Often it's not included. We're going to be using, when we're using optimization solvers, they work well with weak inequalities. They can't handle strict inequalities. Now, if we set delta to be very close to 0, this should have a negligible effect on the game. Fictitious play is an iterative algorithm that is proven to converge to equilibrium in two-player zero-sum game, finite two-player zero-sum games, and it was recently applied to a three-player national security scenario. It's been applied to auctions and other poker scenarios as well. And so our main algorithm is going to build off of fictitious play. In a nutshell, the players, they initialize arbitrarily, often uniform random. At each iteration, it's a self-play algorithm. At each iteration, each player plays a best response to the average strategy of the opponents played so far. And then basically they're going to apply this update rule by averaging in the new best response with the previous strategy. At the end, they're going to output the average of the strategies played over all the iterations. So the main way that the standard classical version of fictitious play involves representing two strategies for each player. The current strategy, which is the average so far, and then the current best response. Now, once we average these to compute the next round strategy, we no longer even need to maintain those two. And so we can interpret the current strategy as a single mixed strategy that is going to select a strategy with this probability. Now, we could alternatively implement fictitious play by, rather than sort of averaging them together and creating a mixed strategy, we can separately store each of the pure strategies that are played and then compute a best response to by maximizing the average or the sum of the utilities against the T pure strategies played by the opponent, which now, why is this seemingly nonsensical? Well, if we have a lot of iterations, if we're on iteration 1,000, we're going to be storing 1,000 strategies for the opponent and optimizing against those, which, if there's only 10 pure strategies, that's, is a waste. However, our algorithm is going to be called redundant fictitious play because we're redundantly storing these strategies. However, if in a continuous game, there's a benefit here because we can compute the pure strategies we can represent. We don't want to represent, we can't even represent a full mixed strategy that puts probability over infinitely many things. So we can represent 1,000 pure strategies, but we can't really necessarily even represent one mixed strategy. And so here, where the pure strategies are, subsets of Rn, for example, here each player selects a certain amount of resource for each of the F battlefields. A pure strategy is just storing number of F real numbers. And so this redundant fictitious play can be applied to continuous games, while the classic version, which operates on the mixed strategies, can't. So now we have this algorithm, we need to figure out how do we compute the best response, which may be challenging. However, often it's going to be straightforward if this pure strategies are compact and utility function is continuous. And even in our case, when it's discontinuous, we have a mixed integer linear program formulation for computing a best response that has a polynomial number of variables and constraints, which I'm not going to get too into. It's in our paper. And so we have experiments on a game. It's going to have 3 battlefields with the value 0.7, 0.2, 0.1, 3 outcomes, each with probability 1/3. Again, we assume player 2 observes the outcome, player 1 does not. We have a budget of 10 for player 1 and a budget of 7 for player 2. We're going to set delta to be this small number, although it's still bigger than the feasibility tolerance. We first ran 5,000 iterations. We computed epsilon every 10 iterations, and we used Garodi solver with 6 cores. Now these values might seem kind of arbitrary, but I was talking to a collaborator and a colleague, and these were the first values that came to his head. So these are sort of arbitrary values that we thought were reasonable. And so we can see here that the exploitability does get quite small. It gets over the 5,000 iterations. It gets down to like 0.03, which is 30% of the smallest payoff. And it goes down, if we run it for 5,000 more, it goes down to like 0.02. One thing worth noting is that the algorithm, about half of the iterations are done within the first 5,000 seconds, and then the next 20,000 seconds are the next half. So the algorithm does get the later iterations are longer because they're solving computing best response against more strategies of the player. The integer programs are bigger, so the subsequent iterations are longer. So to summarize, we have a new algorithm for computing Nash equilibrium in a broad class of continuous games, which include imperfect information and multiplayer. This is very challenging because Nash equilibrium is not even guaranteed to exist, and mixed strategies can put weight on infinitely many pure strategies. We solved a continuous imperfect information model of a Blotto game, which is a very well-studied national security problem. And while it's been studied analytically and there's been algorithms for the discrete case, this is the first algorithm that is solving the continuous case. Thank you.